Hello Math 152 students. In this video we'll wrap up 10.3. We'll take a look at a couple closing comments on this first example, take a look at another example. So in our first example with a small data set, we saw that we had a p-value that was larger than our alpha. We could not reject the null and accept the alternative. We sort of had this inconclusive wrap up, if you will, where we were able to say we don't have enough evidence to say that the calcium levels had changed, but at the same time, we're not saying that they are still 0.11. Be really careful that you don't ever say we accept the null. What we'll say is we do not reject the null, but we don't actually accept the null. In other words, this sample mean doesn't indicate that the averages are still 0.11. It just doesn't indicate that there's enough of a change to say we're sure that we can rule out that it's 0.11 and say it's different. In other words, it's kind of the middle ground. So if you were the researcher in this case, what would you do? 10 data values is not a lot. If you had the ability to collect 10 more, or maybe 30 more, that would help. A lot of times, it is difficult to obtain a small p-value with a small sample size. So, why is that happening? Well, if you have more data, you can think about that as giving you more accuracy in your confidence interval, and then that also translates to your hypothesis test. Having more data kind of gives us a little bit more to go off of when we run our test. Now, we went ahead and looked and made all of that analysis, but I just realized we forgot to do one thing that I should have done with us first. Remember that the book part said we could assume our conditions checked. What I want to show you is that you can verify that if you create those plots when you do your p-value, you'll have a box plot and you'll have a normal probability plot. One downside with this normal probability plot is it doesn't give you the correlation coefficient to check against the table in the back of your book, but in a lot of cases we can look at this and say it's pretty close to linear, I'm not too concerned. If you had a concern about it, you could always go back and do your QQ plot like we did before, and then compare to your critical value table for your QQ plot. Alright, so in an example where they don't tell you your conditions check, look at these first before evaluating your test statistic and p-value. If you had outliers, that can pose problems, and if you had an outlier on your box plot or your QQ plot was very nonlinear, we would probably not want to proceed with interpreting this p-value. It wouldn't be very valid. Alright, so let's jump back to our ebook. And I want us to take a look at number 24 as well. So they tell us a certain brand of apple juice is supposed to have 64 ounces of juice. Because the penalty for underfilling bottles is severe, the target mean amount of juice is 64.05 ounces. Let's stop there. What do we mean about the penalty? Well, keep in mind, they're going to be selling the juice, right? And if customers realize, hey, I'm getting gypped each time by just a little bit, that's probably not good for the company, right? So keep in mind the idea of making a mistake or penalties might have to do with marketing and customer satisfaction. And notice they are targeting the bottles to have a little bit more than the 64 ounces. Probably a good idea. However, the filling machine is not precise and the exact amount of juice varies from bottle to bottle. The quality control manager wishes to verify that the mean amount of juice in each bottle is 64.05 ounces so that she can be sure the machine is not over or underfilling. Keep in mind we expect to have variations from the 64.05, but we want the average to be that 64.05. She randomly selects 22 bottles of juice, measures the contents, and gets the following data. Keep in mind this little icon means we have the data in StatCrunch, so click on that. And that makes our life a whole lot easier. Keep in mind for this one, they tell us a normal probability plot suggests the data could have come from a population that is normally distributed, and a box plot does not show any outliers. So again, most of the time you would want to check this on your own. This is kind of extra that they gave us. So we'll just verify when we get our p-value that this is correct on our plots. And let's take a look at what they ask for A. Should the assembly line be shut down so that the machine can be recalibrated? In other words, if the claim that we're underfilling or overfilling is true, we should shut this down. If it's not, then we could keep running our machine. So sometimes when you have a question like this, you have to figure out how to phrase the everyday language into a hypothesis test. Keep in mind that your null hypothesis always has an equals. So in other words, the base assumption, if nothing is going on and nothing is wrong, is our mean is 64.05. Then the alternative is that it's not. Now here we're worried about over or underfilling. So again, we would want to make this a two-tailed test. If our quality control manager were just worried about underfilling, then you could look at a less than scenario. Right? If she were just worried about overfilling, you could look at a greater than. Okay, now notice the other thing in this scenario is that we're using a 0.01 level of significance, which we'll kind of follow up with in point B, or in part B. So let's go ahead and go back to StatCrunch. Click the wrong thing there. We've got our filled bottle volumes right here. And keep in mind, we could do that QQ plot and box plot first, or we can go ahead and do it with our t-stat hypothesis test. So choose your one sample. Again, here we have with data. If nothing is going on, the bottle should be 64.05 milliliters, or excuse me, ounces on average. And here we want to choose the not equals to. Okay, and let's go ahead and select our box plot and QQ plot. And let's switch it up here and take a look at our plots first. Okay, that looks good. Looks good. Okay, so notice we have some variation going on, but I would say this looks pretty close to linear. So let's go back and look at our test statistic and our p-value. So looking at this test statistic, think about this is similar to t-score, but it's similar to a z-score. This is telling us that our sample mean of about 64 ounces, which is underfilling if we're expecting it to be 64.05, is about 4.5 standard deviations below average if we were expecting 64.05. So this is interesting, and this test statistic is pretty low. So that gave us a really low p-value. In other words, if you're 4.5 standard deviations below what you expect, there's not a lot of area below that on a normal curve. So there's not a lot of area in the left tail. So we've got a low probability of having a test statistic 4.5 standard deviations below. So let's go back and think about what this means for us. A p-value that's less than our level of significance means we should reject the null and accept the alternative. Keep in mind, we are using the 0.01 level, so be careful with your decimals, but this is less than 0.01. Right? This is a pretty small p-value. Sometimes they'll even say a less than if it gets smaller than this. Occasionally you'll see a 0 pop up when it is so close to 0 that it chooses that as its display. But in any case here, this p-value is less than our alpha. So p-value less than alpha means we reject the null and accept the alternative. So we could say there is evidence to support the claim that the filling machine is miscalibrated. So what do we do? If the filling machine is miscalibrated, we should stop the process order a fix, and continue. Come to part B. Explain why a level of significance of 0.01 is more reasonable than 0.01. Notice they give us a hint. Consider the consequences of incorrectly rejecting the null. Sometimes a hint like that seems kind of wordy might throw us off a little bit more. So let's wait on that hint and come back to it and think what our conclusions were. If we reject the null and accept the alternative, it means we need to fix the machine. And a p-value of 0.01 means that we would have to have, a alpha value of 0.01 means that we would have to have a p-value less than that to stop and calibrate the machine. If we changed our threshold to 0.10 for our alpha, that means you could potentially have different data and have p-values less than 0.1 in a lot more cases than the 0.01. So, going back to our ebook here, it says, consider the consequence of incorrectly rejecting the null. If you reject the null, you're going to fix the machine. If you incorrectly reject the null, it means you stop and fix the machine when it really didn't need to be fixed. So what happens there? Let's say you make the wrong decision and there was nothing wrong, but you stop the line, fix the machine. What have you lost? You've lost money because we could have produced bottles of juice to put on the shelf and sell. But you've held up your production and we've lost labor, time, things that we could have used otherwise. So in this case, making the level of significance lower means we're not going to shut the line down incorrectly very often. Okay, is it possible? Sure. But the lower you make your alpha, the less chance of making that mistake. So let's wrap this example up by going back to our slide. I do want to point out that with example 23, we were writing down all of our steps, and then 24, we talked through these steps but did not write them down. On your final exam, you want to make sure you can write down particularly the first step with the setup and the correct symbols. If you are doing a problem on MyMathLab and they don't ask you to fill in the blanks for the null and alternative, practice writing those down, right? If you put a P here instead of a mu, that's going to get you messed up in terms of using StatCrunch correctly and losing points for the setup. So in this case, try going back through this on your own, making sure you can write down all of these steps and that you can also write down a conclusion in everyday language.